All right, so welcome back. Today we're going to have basically a one-off. This isn't a long module, but we're going to be talking about recursion. And then next week we'll get started on our basically our last kind of subject, which a few things, but basically searching and sorting. Recursion is introduced as because conceptually it's used in a lot of problem-solving techniques. But today I'm going to show you what recursion is, how it works, how you can design recursive algorithms, and but ultimately I'm also going to show you why recursion is not necessarily a good thing, and how you can actually avoid recursion. All right. So remember, we are on Piazza if you have questions, or we've got the YouTube chat up. So as a motivating demonstration of what recursion is, what I want to do is I want to put you in a world where you have no loops. You have a programming language like C, but we don't have any for loops. We don't have any while loops. We don't even have any do while loops. How can we sum up the numbers in this array right here without loops? So, ideas? Here's if I were to write a loop, of course, I would write naturally a for loop here, right? I don't have loops though, so I can't do that. I don't have those three loops, but what do I have? I have variables, and I have a function. Okay. All right. Well, I don't know how to use this directly yet, but what if the size of the array was only 1? What if it was only one element? Then what's the sum of the array? I know how to handle that, right? So if the sum, if n is only 1, oops, then what should I return? That element, right? Array of 0. Okay. Now what if it was 2, right? Then that means that, well, I've taken care of this first case where there's only one element in there. Now if there's a second element in there, then how could I use this function over and over again in order to get this one and then add it to this one? Right? Let's go ahead and write a piece of code here that if it's not of size 2, then, well, I don't know how to sum up all the other elements, but if I pass it to this function with a different value, say sum of the array, and if there were 5 elements before, I don't know how to solve that, but what if I take away one element? Right? I don't know how to solve that either yet. What if I take away another element? Right? What if I take away another element and another element until I get down to one element? I know how to solve that because that's on line 6 through 8. Right? So let's back up a little bit here, and suppose again I have 5 elements here. I don't know how to I don't know how to sum these 4 elements, but if I had that sum in my hand right now, then this 5th element I would only have to add it. Right? So if I call the sum on the other 4 elements, or in general the n minus 1 elements, then I would only have to add that to the n minus 1th element, right? And that's my sum. Right? That's it. So you might say, well, wait a second. What do I have here? I have a function calling itself. Right? It's referring to itself. That's what recursion is. It's a piece of code that it refers to itself, that makes one or more recursive calls to itself. Let's actually see this in action right here. Right? Why did I go minus 1 here, by the way? If there are 5 elements in there, then the one at the end is at n minus 1, right? And then all I need to do is do the other ones, right? So I will pass in sum of array and n, and let's see if I get an answer here. And I don't know, I should have pre-computed this, but let's go ahead and see if we get a reasonable answer here. Right? 77, right? Wolfram alpha, oops. Wolfram alpha. The sum of the first 8 primes. Sum of first 8 primes. Tell me what that is. 77. I got it right. Right? Excellent. No loops at all. What I am doing, though, is I'm abusing the stack space for my looping construct. Right? Think about this in terms of if there are only 5 elements in there. That I don't know how to solve the sum of 5 elements. So what I'll do is I'll go ahead and push on top of the stack the subproblem of solving the sum of 4 elements. And then once I've got that, once I've done that, then 3 elements, then 2 elements, then 1 element. This is my stack space, right? I'm abusing the stack space in order to simulate our loop. So that's all recursion is. It's basically implementing a loop without using a loop directly. You're abusing the call stack to do this instead. But we can do coding without loops, right? Pretty cool. In fact, a lot of programming languages, functional programming languages, do this as a matter of practice. They don't even have loops at all in those languages. So that was a good motivating demonstration. What is recursion? Right? So, I don't know. Let's ask Google. Recursion. Did you mean recursion? Yes, I did. Did you mean recursion? Yes, I did. It's a little Google joke that pops up every so often. What is recursion? It's referring to itself, right? So if you look up in a dictionary, what's the definition of recursion? See recursion, right? It's referring back to itself. Of course, I'm sure that in a real dictionary that there would actually be a, like this one, dictionary.com, the repeated application of a recursive procedure or definition, right? So what is recursion? It is basically code. In general, recursion, at least as far as code is concerned, is something that references itself. Right? In coding, it means a function is recursive if it makes one or more calls to itself, right? On hopefully different inputs. Because if you call it with the same inputs over and over again, then you have the Google joke, right? What is recursion? Oh, did you mean recursion? What is recursion? Did you mean recursion? And then you've got an infinite recursion. What happens if you have an infinite recursion in code? You have a stack frame on top of a stack frame, on top of a stack frame, on top of a stack frame. Infinitely, what's eventually going to happen? A stack overflow, right? Okay, so in coding, it's a function that recurs to itself. And this happens all over the place. In mathematics, you have fractals. Right? If you've never seen a fractal before, fractal art, right? Fractal art. In fact, there's a recursive tree of some sort, maybe a Mandelbrot tree or something like that. You've got patterns like this. This is probably some sort of Mandelbrot set here. You've got the Sierpinski triangle, right? Some art made out of Sierpinski triangle, where you take a triangle, then you cut out a triangle in the center and remove it, and then you recurse on those 3 remaining triangles. And you do this infinitely, right? It leads to different notions of dimension. Rather than having, dimension 0 for a point, dimension 1 for a line, dimension 2 for a plane. You can have a dimension somewhere in between 0 and 1, a dimension somewhere between 1 and 2, right? You can have fractional dimensions, fractal dimensions, right? All right, so that's in mathematics. You also have another classic, and this is the one that's always used to introduce recursion, the Fibonacci sequence, all right? And for that, I'm just going to cut and paste the math here. This probably won't render when it goes up to GitHub, but that's okay. There it is. So what does that mean? Well, it's recursively defined. If you have n is equal to 0, then the value of the recurrence is 1. If n is equal to 1, then again the value is equal to 1. But otherwise, what you do is you look at the 2 previous values in the sequence, you sum them up, and that gives you the new value in the sequence. So for example, if I were to actually compute this, right, the first 2, of course, would be 1 and 1, right? That's where you start out. The next one would be the 2 previous ones added together, giving you 2. Now, the next one would be the 2 previous ones added together, which are 1 and 2. That gives you 3, right? Then the 2 previous ones, 5, and you see the pattern here, 8, 13, 21, right, 34, 55, 89, etc., right? ... It goes on infinitely because it's an infinite sequence. This is a recurrence. It's a recursively defined recurrence relation, basically, is what we call these in mathematics. It's simply a what is it? It's a degree 2. I forget the technical term for this. I can't believe I'm blanking on it. But we solve these things in a closed form solution in, say, 235, discrete mathematics, maybe, if you take that next semester. But you can see how you might easily code this, right? Let's go ahead and replace this sum up here. Actually, before I do, no, you don't. I won't include that in the notes. It's just a toy example anyway. What we'll do is we'll create a Fibonacci function that takes n, right, and outputs the nth value in the Fibonacci sequence. Okay, so we'll go ahead and go with 8 here initially, and then result is equal to Fibonacci of n, right? And then we'll print out the nth Fibonacci number here. So now help me write this function. First of all, let's take care of the non-recursive parts. If the input n is 0, then what should we return? 1. If the input n is 1, then we should return 1. So that's a pretty easy piece of code there. If n is equal to 0, or if n is equal to 1, then we'll return 1. This is known as a base case. All right. So designing recursive functions. Right. Every recursive function needs one or more base cases or base conditions in which no further recursion is performed. Why? Just like a loop. If you have a loop, you have an initialization condition, a continuation condition, and then an iteration towards that terminating condition. If you don't have a terminating condition, what do you have? You have an infinite loop. If you don't have a base case in recursion, then you have an infinite recursion and eventually a Stack Overflow situation, right? So this is our base condition. We could also add, flag value or a error handling, right? The Fibonacci sequence is not defined for any n values less than 0. So if that's the case, then we can return a special flag value, -1, right? And then we can integrate this down here, else if, right? So we could also do error handling. Error handling is just a special type of base condition, right? So you may also need to, some base cases may be for error handling, right? Otherwise, you make one or more recursive calls, depending on what you're trying to do, that must make progress toward the base conditions. Right? Does that sound familiar? You have to make progress towards the terminating conditions. Well, that's a loop, right? You have to make progress at I++ or I-. You have to get to the end of the array at some point. Or like we did with our motivating example, you have to get to the beginning of the array at some point. So you have to actually subtract 1 to make progress towards that terminating condition. Again, otherwise you will have an infinite recursion. What is our recursion going to look like here? Well, we make one call to Fibonacci on n-1 plus one call to Fibonacci on n-2, because that's what the definition of this thing is, right? And once we've got that, we can simply return it, and that's it. Okay. So how am I making progress towards those terminating conditions? I'm subtracting 1, at least 1 each time. In the second one, I'm subtracting 2. So both of those are going to make progress towards the terminating condition. Let's go ahead and try it out. GCC, oops, not S, but R. There we go. 34. Is 34 the 8th Fibonacci number? Well, not the 8th Fibonacci number, but index 8, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8. Hey, 34 matches. What if we were to go up to, I don't know, 10? What should it be then? What was it? 89? Right? Hey, that's working, right? What if we were to go up to the 100th Fibonacci number? Right? Oops. Okay. All right, just while we're waiting for that, let's ask Wolfram Alpha. What's the 100th Fibonacci number? So we're going to see really quickly here that it is it's way more than 2.417 billion. So we're going to have overflow here, but we should still be able to compute it, right? I mean, Wolfram Alpha was able to compute that instantaneously, right? So why is it taking us so long? So just wait a couple more minutes. Do you think it'll be done in a couple more minutes? Maybe. Couple more hours? Days? Weeks? Try millions of years doing it this way. Literally millions of years it will take for this to compute the way that we've done this. Why? Think of what it's doing. When you do something simple, I'm going to go ahead and kill this right now. When you do something simple like 5, right? It's almost instantaneous because, of course, it can make all those function calls pretty quick. But think about what's actually happening here. Here I've got a picture depicting from the book, depicting what's happening. When I call Fibonacci of 5, that makes 2 recursive calls. One of them to Fibonacci 4 minus 1, and one of them to Fibonacci 3 minus 2. Fibonacci 4 makes 2 additional recursive calls to 3 and 2. Likewise, this makes 2 recursive calls. Then each one of these makes 2 recursive calls, 2 recursive calls, 2 recursive calls. And you can see that this is going to grow very quickly. This is just 5, so that's 1, 2, 3, 4, 5 levels deep. What if it were 100 levels deep? And it's not going to be a full recursion tree, but basically you're going to have up to, let's ask Wolfram Alpha, 2 to the 100 function calls. How big is that? That much. That many recursive calls. Okay? That's why it's going to take centuries to do this. Right? Literally centuries. Right? If I had a computer that had, I don't know, does anybody want to flex on their speed? Like the 3080 Ti's, how fast are those? Yeah, well, in terms of number of flops. So usually these things are measured in flops, floating point operations per second. So let's just assume, say, 1 billion operations per second. 1, 2, 3, 1, 2, 3, 1, 2, 3, right? 1 billion operations per second. There are 60 seconds in a minute. There are 60 minutes in an hour. There are 24 hours in a day and 365.25 days in a year, right? Now, I don't know if this is an underestimate or what, but there, that many years, right? So let's just say that let's be generous to the 3080 Ti's and say that it's a teraflops, right? That's a trillions of floating point operations per second. Just add on 3 more zeros. Is that really going to take it down to be doable at all? No. You still have 10 to the 10 years of work to go, right? You can't just upgrade your hardware and solve this problem here. You are making an exponential number of function calls, and that's why it's never going to work this way. Not only that, but we can observe something else here. How many times did I make the same function calls over and over and over again? Fibonacci of 2, it's right there. Fibonacci of 2 is right there. Fibonacci of 2 is right there. I made 3 calls to the same input. What about Fibonacci of 3? I made 1, 2 calls to Fibonacci of 3. How many calls did I make to Fibonacci of 1? 1, 2, 3, 4, 5. Right? Do you see a pattern there? The number of recursive calls matches the Fibonacci sequence itself. And that's why the Fibonacci sequence grows exponentially. In fact, you can have a closed form solution using the golden ratio phi of 1.6, right? And amateur mathematicians like to give it all sort of mystical power and stuff like that. That it's the perfect ratio or whatever. Don't worry. Don't buy into that garbage. All right? But anyway, this is why the Fibonacci sequence is usually introduced with recursion, because it's simple, it's straightforward, it's easy to demonstrate. It's a terrible example, though. Why? Because if you do it that way, then you will have billions and billions of years of computation. I think it's the perfect bad example because it illustrates exactly why you shouldn't use recursion. Right? What's a much better way of doing this? Don't go top down where you start with n. Go bottom up like we did here. If you want to compute the nth Fibonacci number, the 8th Fibonacci number, for example, right, 34, then start with two variables. One of them to keep track of the current, one of them to keep track of the previous. And then just simply add those two together to give you a new one, right? And then move your other variable over. Do that as many times as you need until you get to the value that you want. Right? Just a simple for loop, right? And that's why recursion has its costs. That if you do it naively, you end up doing an exponential amount of work, and you end up doing a lot of extra work, duplicating your work. One, doing this over and over and over again. Okay. So, from that, from that idea, let me put on my devil's advocate hat here. And recursion, is it good or not? Right. So, why do we even have recursion if we have those kind of consequences? Recursion can be a useful and good tool, right? You can think of problems in terms of coming up with a recursive solution, right? So there are many divide and conquer style algorithms that that are presented initially as recursive algorithms. But guess what? At the end of the day, for example, we're going to look at some quick sort, merge sort. A lot of sorting algorithms use recursion by dividing a list. Say, for example, merge sort. You've got an array here, and I don't know how to sort this, but I can divide it up into two arrays, and I'll sort this one, and then I've divided it, and then I'll conquer this one. I'll divide it again and conquer it now. I'll divide it again until you get down to one element, and guess what? One element, by definition, is sorted. Now all you have to do is, given these two arrays that are sorted, all you have to do is merge them together by zippering them up, right? And that's how merge sort works. It's a divide and conquer style algorithm. And so another example that we'll look at is binary search. If you've got a sorted array, you don't need, and you want to search it for a needle, in this is our haystack, you want to search it for a needle, look at the middle element. If the element that you're looking for is larger, then that means that it exists in this half, meaning that effectively you've cut out half the list and thrown it away. You've divided it in half, and now you only have to conquer half as big. Right? And that's why it's a very useful tool for thinking algorithmically, for thinking about ways to tackle problems. Many functional programming languages, for example, Haskell, Scheme, if you're familiar with these, use recursion as the normal, as the default way of computing things. Right? Now, they get around this work by having what's called lazy, not lazy loading, lazy computations. Basically, they don't actually do the entire thing. They use what I'm going to show you here in a moment, called a technique called memoization, which is basically just caching. But you do have programming languages that completely discourage the use of traditional loops. In fact, some programming languages don't even have loops at all. Right? Recursion can also lead to simple, clean or beautiful code, right? That is easily understood. I mean, there's no misunderstanding this code over here, right? That's as simple as it gets. A for loop with two variables and a temporary variable, that might be a little bit harder to understand, but this has a direct translation to code from the mathematical definition up here, right? It's really, if you understand this math up here, then it's really easy to understand this code over here. You don't even have to know how to code to understand that it's probably computing this thing over here. The problem with these three things, simple, clean, beautiful, easy to understand, four things, I guess, is that they're all subjective, right? There are plenty of objective reasons to argue against recursion, and that's where the bad comes in, right? So, recursion, the bad, right? Recursive functions essentially abuse the stack space. And if you have limited stack space, good luck, all right? In fact, there are some organizations that ban the use of recursion in code, NASA being one of them. The NASA style guide says no recursive algorithms in our, no recursive code in our code base because it risks a stack overflow. We've got a lot of embedded systems, a lot of mission critical systems. We can't risk overflowing the stacks. So avoid that, right? Think of something better, right? At least with those style guides. There are risks for stack overflow for deep recursions. And I say deep here, but like you already saw that 100 levels deep is not deep at all, right? 100 function calls at most. You're not going to hit a stack overflow with 100 function calls, but you are certainly going to start hitting exponential work, right? You risk recomputing values over and over, right? You risk on a naive amount of exponential work. And again, some organizations have even banned recursion in their code bases because of this. NASA being one of them. So how do we go about eliminating recursion? Right? So first of all, in general, recursion is not necessary. Right? It's not necessary to a programming language. In fact, some programming languages don't even support it. Earlier versions of, I think, Pascal or Fortran or something did not allow you to have a function that called itself. It just wasn't part of the language. Most languages do support recursion nowadays, but some of them, you can take any recursive function and you can rewrite it and simulate the recursion. You can take any recursive function, right, computable recursive function, and write equivalent code that either uses a loop or simulates recursion. So merge sort, that algorithm that I was talking about, or quick sort, C has a Q sort implementation, but I've never seen an actual implementation that uses recursion. Some implementations use recursion up to a point, but then they switch over because recursion is actually expensive. Making all those function calls needlessly, it comes at a cost, right? That cost is not necessarily there if you have a traditional old for loop or something like that, right? Another way that you can do this is you can also use memoization. Now, this is a new term. It is not memorization. I did not mispronounce that. I did not misspell it. It is memoization. I forget why they called it that, but basically, it's the following strategy. If you need to compute a recursive value, go ahead and go ahead. Right? If the value has not already been computed, pay for the recursion. In other words, just go ahead and do the recursion. Right? But once you have computed the value, store it in we call these things caches. Right? Spell it right though. In a cache. A cache is simply, like a cache of weapons or a cache of goods, right? It's just a storage location. You store it off so that you don't have to recompute it again, right? If the next time you want or you need to compute the value, you don't pay for the recursion, right? You look it up in the cache. Right? So what does that look like from the perspective of this over here? Once we've computed Fibonacci of 3, then we've stored that up. We pay for the recursion down here. we're going to end up having to do this entire recursive tree or something like that, right? But once we've stored the Fibonacci of 3, which is 1 plus 1, or what was it? 1 plus 1 and then 5, I think it is, right? 0, 1, 2, 3. No, it is 3, right? So once we've computed the value of Fibonacci of 3, which is 3, we store that off into a memory location. Then the next time we need to compute it, we don't do this entire subtree. Instead, we just simply pull that out of the memory location, the cache, and use it. Effectively, what we've done is we've cut out this entire tree. When you cut out with that branch of the tree, what is it called when you chop a branch off a tree? Nicely, that is. You're trimming the tree. You're also pruning the tree, right? So you can basically trim this tree down into, well, down to basically just one branch, right, with a bunch of leaves hanging off of it, and that effectively cuts out most of the exponential nature of this tree. To demonstrate that, I want to actually show you how to do memoization, because that's what you're going to be doing in your hack next week. Okay. So this is the Fibonacci sequence that's recursive. I'm going to go ahead and rename this to be recursive, right? Then what I'm going to do is I'm going to make another one, Fibonacci memoization, right? Int n. Okay. Now here's the idea. What we need to do is we need to maintain a cache, or a table basically, where we can put in values that are the result of this recursive computation. We could, of course, seed it with the first two values, right? Because those are the base cases. If it's 0, if it's 1, then we can put those into that cache, okay? So what we need to do is, assume that we've gotten this cache already. Int star table, I'll call it table, because that's what it is. It's a table of values. That table sub 0 is going to have the value of the 0th Fibonacci number, which is 1. Table sub 1 is going to be 1. Eventually, table sub 2 is going to have the value 2 in it, right? Dot, dot, dot. What are we actually interested in here? We are actually interested in table sub n, where n is our nth Fibonacci number, okay? So, how do we go about doing this? This is our table. I check the table first. If table sub n is something, has been defined already, right? Has been computed already, then use it. Return table sub n, okay? Otherwise, else, the Fibonacci of n has not yet been computed. So pay for the recursion. Right? And by paying for the recursion, I'm not going to use this down here, because then I would just be back at square one. I'm going to recursively call this, this function on n minus 1, passing through the table, and then adding up n minus 2, a call to n minus 2, passing through the table. I don't return that, right? I don't return that right away, because I want to actually store that result. And once I've got the result, I put that into the table. So table sub n is equal to result. Then I can return the result. Right? And do you see how that works? Once it's in the table, the next time I make this recursive call, table sub n will have computed it already, and I can simply just use it. Now, this is obviously not real code. How do I go about defining whether or not the table has already computed it? Right? I can put in flag values. What's a good flag value? Right? Something, a flag value that indicates this thing has not yet been computed. Could I use 3? No, because that's an actual value. Could I use 1? Well, no, because that's an actual value. I could use, say, 12, because 12 never appears in the Fibonacci sequence, but that's kind of weird, right? So what kind of flag values should I use to indicate that this thing has not yet been computed? How about 0? If it's not equal to 0, then I know that it's been defined, right? What's a better way of writing this? What about just like this? Why? Because 0 is false. Anything else is true. Right? Cool. I'll go ahead and leave it in here because this is a lot clearer though. Right? That's kind of like a trick, and tricks are for kids. We don't want that. Right? All right. So what would main look like now? I want to compute the nth Fibonacci number. So I need to create my table, right? Int table, right? The star table is equal to a call to malloc. How big of a table do you need though? Size of int times, would it be just n here? No, it'd be integer times n. What, say again? Integer times n, right? Size of int times n, but also the nth Fibonacci number, if I want the fifth one, 0, 1, 2, 3, 4, 5, right? Because I'm starting at 0, I need all the way up to and including n. So I need to go one more. Right. And be careful, because we have seen people still doing math like that, and that's definitely wrong. You're getting away with it with as far as strings go, because characters are only ever 1 byte, so mathematically it's equivalent, but it's still not a good idea to do it that way. This is these two are definitely not mathematically equivalent, because an integer is going to be 4 bytes. That plus 1 needs to be times size of int to give me those 4 bytes. Okay. Then what I'm going to do is initialize the table to flag values, indicating that the value has not yet been computed. Right? Okay. So that means for int I equals 0, I, in this case, I is less than or equal to n, because I made it n plus 1, I plus plus. Table sub 0, or sorry, table sub I is going to end up being, what was our flag value again? 0? Right? You could go -1 if you wanted to, something like that. And then what I'm going to do is I'm going to take care of the base cases immediately. Care of the base cases. Table sub 0 is equal to 1. Table sub 1 is equal to 1. Now, if you wanted to, you could really, you could go whole hog and, compute the first 10 of them and store them off into a table, right? And then you never have to do the lower 10 ever again, right? But we won't do that. Instead, we'll just go ahead and do, that's recursive. I'm going to have to cut and paste that out here to get it to compile. What I wanted, though, is this one. Fibonacci memoization of n and the table. Right? We can actually look at the contents of the table later on to see that it's actually doing this, but this should be good enough. All right, oops. Plus plus, I plus plus. There we go. So I still have 8, right? Or 5, I guess. And so what's the sixth Fibonacci number? The one 0, 1, 2, 3, 4, 5, and we get the same result here. Now, what if I went with 10? Right? Then I get 89. So it looks like it's correct to me. What if we did, -1? Then I never did any error handling up here, so that's going to fail, of course. You could check the corner cases like 0. That should output 1. That works, right? I'll let you go back and compute take care of the error handling. But now 100. Now, first of all, we're not going to be able to get an answer out of this, a correct answer out of this. But at least we get the wrong answer. But at least we get the wrong answer fast, quickly, right? Why do we get the wrong answer again? What's the 100th Fibonacci number? Some very, very big number that is not going to be representable by an integer. That's okay. Let me show you a trick here that you're going to do next week in your hack. I'm going to change this to a long. A long is a 64-bit integer. It can represent values up to 2 to the 63 because you need 1 bit for the sign, -1. So that looks like it might be able to support the 100th Fibonacci number. I'm not sure. Let's go ahead and try it, though. I'll change the return type to a long. And that looks good. Oh, the result has to be a long. And then down here, and this table has to be a long. And we might technically need to put that in there. I'm not sure. That one as well. The L just indicates that it's going to be a long 0 and a long 1. And then finally, I think that this is going to be LD for long. Let's find out. Oh, this one needs to be a long. There we go. All right. Argument is of type long. Oh, because I didn't change this up here. This should be long too. There we go. There we go. Now the 100th Fibonacci number. It's still probably going to be overflow there. Yeah, that's not big enough. So we can go with 50, something like that. There. That's certainly small enough. What's the 50th Fibonacci number? I'm not going to go look at all the digits, but it's going to be 1, 2, 5, 8, 6, 1. Oh, no. We might be off by 1 here. Oh. No, 51st. Apparently they start their indexing at 1 instead. Okay, fine. That's just off by 1. 20365, 20365. I'm satisfied that that's the same. Right? And of course, if we wanted to go even larger, then we would have to bring in a library to go beyond 64 bits. GNU's multi-precision library, like GMP. The GMP library would allow you to have arbitrary precision numbers. So as big of a number as you want, it'll just allocate more and more memory for it. Of course, then you pay a price for that because all the computation is now done in memory in software rather than on hardware. All right. So that's memoization. Instead of repeating all this stuff, you store it off into a table. And then you use that value, and if it's not there, then of course, then you have to pay for the recursion. You do the recursion, but before you return it back to the calling function, you put it back in that table and then pass that table around to all your function calls. Essentially, it cuts out most of this table. The recursion now looks like a nice single branch. Basically, you've pruned the tree out so that you've cut off all the branches, and now you just have a stick, right? And that's it. If you want to look at it like a tree. All right. So, that's my quick introduction to recursion. I'll mention that in Hack 12, Hack 11 this week is still on encapsulation. You'll basically be making your own structure from scratch to represent, I think, an airport. And then you'll be doing some stuff that you've already done, say, I think from Hack 2, where you do air distance calculations between two airports. And then you'll use that again when we do searching and sorting. So, but Hack 12, basically you'll compute how long it would take to compute binomial coefficients recursively. Right. So what are binomial coefficients? And here I'm going to introduce some more math here. Has anybody, hopefully you've seen this before. That's read n choose k. Right? That's read n choose k. Right? It's equivalent, it is the number of ways to choose k elements from a set of size n without repetition, without consideration on the order. Right? So for example, say that I had 4 things. I had 4 people, and I needed to choose 2 of them for teammates or something like that. How many ways are there of doing that? I could choose the first 2. I could choose the second 2. I could choose the first and the last. I could choose the second and the third, right? I could do these 2 or these 2. How many ways are there of doing them, right? If I had, I don't know if Wolfram Alpha will generate these. A, B, C, D, choose 2. If I had Alice, Bob, Charlie, and Donovan, how many ways are there of choosing 2 of those things? There are 1, oops, no, that's not it. Roots, I don't want roots. A number of, all right, it's not going to do that for me. But you can imagine how many ways are there of choosing them? Well, I could choose A and B. I could choose A and C. I could choose A and D. I could choose D and A, but guess what? That's the same thing as AD. Make sure that these are not, yeah, this is not covered up. So what else can I choose? I can choose B, C. I can choose B, D. I can choose C, D. There's 1, 2, 3, 4, 5, 6 ways of choosing two things from a set of size 4. In general, N choose K, that's going to be equal to, well, if you want to look at it one way, it's going to be N factorial. What is factorial? You've done that before in your programming. N factorial is, like 5 factorial is 5 times 4 times 3 times 2 times 1, right? And it's huge. That's super exponential. That's even bigger than exponential. And then N minus K factorial, K factorial. That's the easy way of computing it. That's the straightforward way of computing it. Here's the hard way of computing it, using Pascal's identity. This is the hard way, but this is also the recursive way. Okay. It doesn't know what's binomial. Okay, fine. What is it? I have to remind myself. Pascal binomial identity, or theorem, or whatever. Pascal's rule, apparently, maybe. There we go. We want this on the right-hand side, so that on the left-hand side there. That's going to be, let me put it in the notes if you really want it. It's going to be N minus 1 choose K plus N minus 1 choose K minus 1. Right? So this is the recursive version. To compute the binomial coefficients, all you have to do is make a recursive call. Now you've got N and K, so you've actually got 2 inputs. All you have to do is call it on N minus 1, same K, and then call your function on N minus 1, K minus 1, and do it recursively. But you'll find out, if you do that, that you're going to end up with astronomically long computation times. First of all, these numbers are too big, so you're going to have to use longs anyway. But you will be computing this for centuries if you use Pascal's identity here. If you just use this, it'd be done in a matter of seconds. Or if you use memoization, which you will be doing in the hack, then it can be done instantaneously. Now be careful here, because the table is actually going to be a 2-dimensional table. It's going to be, you have two input values. You have N and K. So if you think of N as the rows and K as the columns, then you can start filling out this table. Now it is actually a full table, because you've got rows and columns. Rather than the example that we just did, the Fibonacci, that really wasn't a table. That was just an array. So it was a 1-dimensional table, right? But that's what you'll be doing in Hack 12 next week, all right? Getting some exposure to doing recursion, writing recursive functions, realizing that this is probably not the way to go for a lot of programming applications. How can we avoid it? Well, we can avoid it by not doing the same work over and over and over again. Put it into a cache and save it. You'll find that even if you're not doing an exponential amount of work, this cache trick is used all over the place. Don't compute things twice in your program. If it's something that if it's a value that you might need again, store it off into a cache, right? And then you're not paying for the computation anymore. You're paying for the memory instead, right? So it's kind of a trade-off. You don't need to store anything at all if you're willing to recompute it every single time you need it, right? But if you're willing to pay for the memory and store it and save it, then you can save on computation. So it's a trade-off. Are you going to use more memory, less computation, less processor, or more processor, less memory? Right? You can trade off like that. And this trick happens all the time in engineering, right? And in computer engineering, computer science, whatever. Right? All right. Any questions? Otherwise, that didn't take it long at all. Yeah?
Is the memoization as fast as the for loop? Is there a
I'm sure that the for loop, for Fibonacci, the for loop is going to be way faster because you don't even have to store anything at all, right? The memory footprint would be a lot less. I mean, we can try it. Let's see. Time a dot out. Okay, so system it's going to be very, very small anyway, 0.001. But let's go ahead and get rid of this stuff, and let's try it. So remember that it only took 0.001 seconds. Int a b or long previous, current, and temp, right? And previous is going to be 1, and current is going to be 1. So I'm seeding those two with the first two initial ones, and then just a simple for loop here for int I equals. We'll start it at 2 because we've already computed the first two. I is less than or equal to n I plus plus. Temp is going to be equal to the previous plus the current, right? Then we take the current and we put it into, take the current and we put it into previous. So current, previous is going to be equal to current. And then we take this temporary value, which was the sum of these two, and we make that into our current. Current is equal to temp. Right? Okay. And then we print out the current once we're done. Remember this 20365, just to make sure that it's correct. What are you talking about? Temp? Oh, duh. Okay. Now I forget what the number is. That looks right. Time a dot out. Oops. All right, we're not even registering any time now. So I imagine that if you went even larger, like 1,000 or something, then yeah, you'd start to notice it. But it's going to be very, very tiny. It's still a linear algorithm versus another slightly larger linear algorithm. If we're going to eventually get into algorithms and algorithm analysis, especially in computer science 2. Both of these things are going to be linear algorithms. In other words, the performance scales linearly by a linear function. But the first one might be, 2n, and so it's got a steep slope. The other one would just be, say, n, and so it's got a less slope, but these slopes are the same thing, right? So from that perspective, they're equivalent algorithms, equivalent complexity, but of course, since this one has a slightly smaller slope, then it has a different coefficient out front, so it's slightly faster, right? And that's, yeah, okay, there, now it was perceptible. You'd have to, and if you're going to empirically analyze algorithms like this or analyze code like this, you'd want to, of course, run it 100 times and then take an average or something. But yeah, it's probably going to be faster, I imagine, because you're not setting up memory, you're not cleaning up memory. All right. Any other questions? Sorry, let me check online here. No questions on Piazza. Oh, message retracted. Okay, on YouTube. Hopefully, it was just something that we answered successfully rather than something. No, I didn't mean to put that in there. Okay. Well, then again, for the rest of the semester, what are we looking at? You've got 3 weeks left, right? As far as topics go, where are we? File I/O, encapsulation, recursion, of course, this week / next week. And then we're going to get into searching and sorting. That's our last topic. And that's going to take the next 3 weeks because we're going to get into it rather deeply in that we are going to look at it from an algorithmic point of view. Then we're going to look at it from a practical point of view, both searching and sorting, because we're going to actually use all those tools for your project. Your project involves everything that you've learned up to and including that stuff next time, or next in the next couple of weeks, where we've got a bunch of financial data. It's all mocked financial data, but you're going to be running several reports on that data. It's transactional data, so it's got bank accounts, transfer this amount of money to this bank account, which has this balance afterwards, right? So it involves file I/O because you have to load up the data. It involves encapsulation because you have to represent the data. It involves searching and sorting because we're going to ask you to do certain, operations on that data, like searching through for suspicious activity, searching through and trying to detect potential, fraud. The number of records that we have is in the hundreds of millions. If you don't have efficient algorithms, no way are you ever going to be able to compute anything on that data set. You are going to be, if you do things naively, then you are going to be stuck in this large exponential tree. And it'll take you, weeks, centuries to actually compute this stuff. But if you use the proper tools, right, searching and sorting techniques, then it should be immediately computable. Right? All right, and then we've got the week 14 is the wrap up where you do have lab 14, lab 15, which have been cut because of the updated COVID schedule. If you want to, go ahead and check them out. They're not for extra credit or anything, but they do provide a nice bookend to the next semester, especially with databases. If you're going to continue with computer science 2, right? All right. That's where we're going for the rest of the semester. You still have about a third of your assessment to go, including that 100-point, where is it? That final project, 100 points due during the final week. This hack, actually, you use the results of this hack in your final project, so you can collaborate on the hack. You just can't collaborate on the actual project. And then, of course, we've got our final exam. Somebody asked about it on Piazza, when is it? And I looked it up, and tentatively it's going to be that Tuesday. You will have at least 24 hours to do it, just like the midterm. It'll be open book, open note, open computer, of course, no collaboration. It's worth 100. It's worth 100 points. I think it's worth 150 points. I think that's a typo. I'll have to double check on that though. And so you still have about a third of your assessment to go, but a large chunk of it at the end is non-collaboration. Right? We have to test whether or not you've actually learned the stuff for yourself rather than just learned how to be a very, very good collaborator with somebody else. Right? All right. Still no questions online? Yeah, go ahead.
So you said like the results of hack 1 are used in the project?
Hack 14.
Or hack, sorry.
Yeah.
The part 1.
Sure.
Would you suggest, so would you still be able to start the final project given, like...
You're going to have to do hack 14 before the project. I mean, you can probably, you'll end up doing hack 14 to do the project anyway. Right. So yeah, if you want to, you can start on it right after hack this upcoming hack, because this hack is just basically searching and sorting, or this hack is encapsulation, making the structures that you'll need to model the financial data, and then some comparators and stuff like that. So what you do in hack this week. Where is it? Hack 11, you're doing this for an airport. And then in 2 weeks, you'll be doing hack 13, which you use airport again. You'll be doing searching and sorting algorithms on the airport data. Basically, all that's repeated, but for financial data in hack 14 here. Okay. All right, have a good weekend. There's no game. Oh, will the class on Canvas close at the end of the semester? No, and not as far. No, it remains open. In fact, I think if you go to the GitHub page, you can look at the last 3 years of classes. Right? As far as a grade book goes, I'm not sure. They might freeze the grade book, but they do dump classes, I think, after 5 years. So. You won't have the classes in perpetuity. I mean, they'll back them up, but they won't be publicly available after 5 years or something on Canvas. Right? Okay. All right. then have a good weekend. Unfortunately, there's no game, of course, and baseball is over, so there's nothing to do, right? You should be able, you should be able to do your hack this week without anything standing in the way.